When humans first invented numbers for counting, or some would say discovered numbers, we really only needed to count a whole number of things. So, like the number of apples in a tree, or the number of cows that we have, and so on. And those were really the first numbers, right? The natural numbers. So that's what they look like here. They have this n, which is the set of all of the natural numbers. And this is pretty self-explanatory. There's no need to overcomplicate it. It's just all the numbers that you would naturally think of, like 1, 2, 3. And there's nothing really weird or unintuitive going on in here. But eventually we needed more numbers. Okay, so note that 0 isn't in this set because it seems weird to think of 0 as a number you would think of naturally. Now, some people would argue about that. But as I said, we need more numbers other than this to do sort of interesting or more complicated things. So the first one was the concept of debts, or owing people money, and that's where negative numbers came in, right? It doesn't really make sense to take 5 cows away from 3 cows and be left with negative 2 cows, because that's not natural, right? But we needed negative numbers when it came to sort of debts and owing people money. You have an overdraft, you have negative money in it. We'd say these are today quite natural. So once you include negative numbers with the natural numbers, you call this the integers. It's a big Z or Z, depending where you're from. And that was interesting. So notice that we got the integers from the natural numbers, because if I subtracted, say, 5 minus 3, well, that's 2. That's fine. But if I go 3 minus 5, I couldn't do that if I was just working in the natural numbers. So I needed new numbers. I needed a negative 2, right? So that's an integer. Now, I still can't do everything because, well, that fractions exist, right? So once we add fractions on top of all of that, then we have sort of what you might think is a complete number system on the offset, right? So for example, if I'm just working in the integers and I go 5 divided by 2, I don't know what that is. I don't have an integer that tells me the answer to that. But I do have a fraction. And these are called the rational numbers. Okay, the rational numbers. And you may think we're done there, but we're not. There's also more numbers on top of that, which is quite interesting. So, I mean, here's sort of a pictorial representation of where we're at the minute. We have the natural numbers. Once we add the negative numbers, we're now in this green ring, and we are in the integers. And then once we add all the fractions, we've got the rational numbers. So note that you could say that 2 is a rational number because it is included in this blue circle, right? Everything that is a natural number is also a rational number. Everything that is an integer is also a rational number, okay? And this is where Pythagoras assumed that we were done, because he thought that fractions were like really, really, ratios were everything, right? But it turns out that there exist certain numbers that you can't actually write as fractions. So that is the big bombshell there, right? So, for example, pi is not a fraction. You can't write pi as a fraction. It's an infinite decimal expansion that goes on forever, and we can't really do anything about that, right? There's no fraction. Some people approximate pi as 22/7, but that's an approximation. That's not exactly pi. And another number, we could do this in another video. I could show you why this is true. We take 2 is fine, but the square root of 2, I can't actually write that as a fraction either, and I will prove that to you in a later video. But there do exist numbers. Another one is e, which is used in exponential growth. It appears all over mathematics. Euler's number, something like 2.71882 something something. I should probably know more places to that, but I don't. Okay, so that to complete the set of numbers, we of real numbers, if you will, we then have to add these irrational numbers in. So I will denote that by the set of R. So R is everything that you see here, plus these irrational numbers that can't be written as a fraction. Okay, so let's test that you guys got all that. So 3 questions. Let's just say some true false statements. Okay, so 3 is an integer. Okay, is that true or false? And it's actually true, because 3 is a natural number, but it's also included in the integer, so it is an integer. And it's best to just use these terms to describe certain numbers until they appear natural to you. Pardon the pun. Okay, root 2 is a rational number. Root 2 is rational. Is that true or false? It is not true. As we discussed up here, you can't write it as a fraction. So anything that's rational, you can write it as a fraction. And if you can't write it as a fraction, it's irrational. Okay. What about 0? 0 is a rational number. Well, that's true, because it's an integer, so it has to be a rational number. Finally, let's say a half is an integer. And that is not true, because integers are only negative whole numbers and whole numbers, right? So that one's false. And just to get our head around rationals and irrationals, you know, another little example here. Root 2 over 4. Is it a rational or an irrational number? You might think it's rational because this looks like a fraction, but remember that root 2 itself isn't alloyed, right? So it can't be written as a fraction. So when I say fraction, I really mean fraction of 2 whole numbers. So this one is definitely irrational. Irrational. Okay. Right, so that's about it. Let me just pull up a question I stole from one of the new specs. So this is question 16 on paper 1 of the sample paper. So what does it say? A student argues that when a rational number is multiplied by an irrational number, the result will always be an irrational number. Identify the rational number for which the student's argument is not true. Okay, so the student thinks that if a rational number, let's say, I don't know, a half, is multiplied by an irrational number, let's say root 2, it'll always be an irrational number. Seems reasonable, right? And your question is, well, there is one rational number, or their rational numbers, so they've kind of given you away. There's only one rational number for which this doesn't work, right? So I have some rational number, let's say x, and I'm going to times it by some irrational number. Let's just pick root 2 or root 3 or whatever. And the result I'm left with can't be irrational, right? I'm looking for a number that will break that. Okay, I want to get something that's rational. And, well, you think about it for a bit, and then you realize that, you know, any real fraction I put in here, it's going to give me some multiple of root 3 of some sort, right? I know that x times root 3 is x root 3. This will always be irrational, except when what? You know, when would this be able to be written as a fraction? You could imagine x being root 3, and then I have root 3 times root 3, which would give me 3, which works. But remember that x has to be rational, so that's not allowed. And I don't know, man, this question's really just a trick. Once you spot it, you're like, oh, okay. This will work when the number that you multiply by is 0, but no other number. And again, we're going to go on to proofs. You know, can I prove this statement up here? That's the next part of the question. And I'll do a new video on proofs and why root 2 is irrational and so on, just to give you a bit more understanding. But for now, we're just really introducing you to these new concepts of naturals, integers, rationals, and irrationals. Okay, guys, any comments, please leave them in the videos comment section. Sorry, any questions, please leave them in the comment section. I'll do my best to answer them. I hope this is useful to your mathematical endeavors of getting good marks in these A-level exams. Okay, thanks for watching.